The internet glances so far away that it is catching light that has already been traveling for over 13 billion years. However, the universe has grown, and as a result, the light has been spreading farther. The farthest worlds we're considering go all the way back to the Big Bang. The vastness of the universe might appear immense, but it began in its entirety from our reference point, the singularity. This is how we currently operate. It might put the Big Bang theory in perspective. Anyway, the James Webb Space Telescope JWST has shed light on important mysteries concerning the formation and growth of the universe. These findings leave us speechless. The renowned physicist Brian Cox declared that the significant findings of the JWST could actually alter our perception of the entire universe. Join us as we explore these brand new heavenly discoveries that promise to alter our understanding. The name of the James Webb Space Telescope, named after the well-known NASA executive. James E. Webb is still a marvel and currently underway galactic investigations. The telescope is an enormous mechanical leap ahead of its predecessor, the Hubble Space Telescope. As a result of a collaboration between the European Space Agency, NASA, and the Canadian Space Agency, the JWST surpasses its predecessor in many ways. It makes use of cutting-edge technology and improved design for focusing on the universe in incredible detail. Unlike Hubble, JWST conveys sharp images of faraway celestial bodies and primarily operates in the infrared range. This fascinating component allows it to penetrate astronomical debris and discover divine objects that were previously hidden from our view. With its enormous mere 6.5 meters, essential length and composed of 18 hexagonal segments, the JWST is far more powerful than Hubble's reflector. It orbits Earth at a distance of 1.5 million kilometers, positioned at the second Lagrange point L2, in harmony between the Sun and Earth, ensuring a constant and steady view of the universe. Seeing the farthest reaches of the universe involves not only traveling through light years, but also entails a kind of time travel. The JWST observes, with its infrared instruments, things and events from the heavens dating back thousands of and billions of years. The light from these things, as a result of the expanding universe, moves through a red shift from the visible to the infrared range to longer frequencies or wavelengths. Infrared light can be identified by the JWST even when emitted by celestial bodies at extreme distances, giving researchers the ability to investigate star formation, the evolution of cosmic systems, and the atmospheres of exoplanets. One of the most recent historic discoveries includes the location of an incomprehensible collection of cosmic structures at the outermost observable edges of the universe. This finding challenges the theory's veracity and the circumstances of cosmic evolution, leading to a re-examination of our primary cosmological assumptions. To gain a deeper understanding of how we reach this point, we ought to take a brief tour through the history of space exploration. Ancient civilizations, like the Chinese and Greeks, laid the foundation for planetary understanding by observing celestial bodies in motion. Regulations devised by Newton in the 17th century provided a theoretical framework for space structure. In the middle of the 20th century, the influential astronomer Edwin Hubble made historic cosmological discoveries. His observations revealed that nebulae were distant, isolated galaxies. Changing our understanding of the Milky Way and the size and expansion of the universe, Hubble's law demonstrated that galaxies farther away were receding faster, thereby proving the universe is expanding. Post-World War II space exploration marked the beginning of the space race, with the Soviet Union's Sputnik in 1957 as the first orbiting artificial satellite. Milestones followed: Yuri Gagarin's journey into space in 1961 and the Apollo 11 moon landing in 1969. Fast forward to 1990, the Hubble Space Telescope was launched, providing remarkable clarity and insights into the cosmos. From ancient observations to technological marvels like the James Webb Space Telescope, we see a constant improvement in our ability to understand the universe. The HST revealed the boundless nature of space and reshaped fundamental ideas in astronomy. For example, it captured the famous Pillars of Creation image in the Eagle Nebula, revealing a stellar nursery made of towering gas and dust columns. Another important achievement was Hubble's deep field image, revealing thousands of galaxies. In what appeared to be empty space, the HST also explored exoplanet atmospheres, detecting organic and water-based molecules on distant worlds, hints of potentially habitable zones beyond our solar system, with the help of observations of the most closely monitored supernova, SN 1987A. It also shed light on the life cycle of massive stars. These accomplishments firmly established the HST's legacy as the foundation of modern cosmology. Its replacement, the James Webb Space Telescope, was launched to further develop these achievements and lessons learned from prior missions. Our current understanding of the universe's beginning, 13.8 billion years ago, is that it emerged from an incredibly hot and dense singularity, rapidly expanding and giving rise to energy, matter, and fundamental forces. As the universe grew and cooled, it led to the formation of atoms, stars, galaxies, and the large-scale structures we observe today. The Big Bang Theory also explains the cosmic microwave background radiation, the immense scale of the universe, and its elemental abundance. Although now widely accepted, the Big Bang Theory initially faced skepticism. Competing models like the steady-state theory posited a universe without a defined beginning. Questions surrounding the singularity and early expansion raised concerns. Over time, many of these objections were addressed. A major piece of supporting evidence was the 1965 discovery of cosmic microwave background radiation. Further space missions like COBE and WMAP strengthened the theory. Today, the JWST, with its state-of-the-art instruments, looks through cosmic dust in the infrared spectrum, capturing the universe's earliest light and observing object formation soon after the Big Bang. Its capabilities allow it to focus on stellar nurseries and the formation of stars. Invisible to the naked eye, infrared light, with its longer wavelength, penetrates dust better than visible light in an area where Hubble had limitations. The JWST can observe cooler objects that emit primarily in the infrared, making it ideal for studying phenomena like brown dwarfs, distant exoplanets, and remote galaxies. As celestial bodies move away, their light waves stretch redshifting, making infrared observation crucial. Stretched, resulting in a lengthening redshifter wavelengths. The JWST's infrared capabilities can detect these redshifted signals, taking in light from the beginning of the universe and providing insight into its development and formation. Events that are active, like mergers of black holes or the primary emission from new star births, occur in the infrared range. This increases the investigative abilities of JWST. The telescope can look into things that would otherwise be concealed or unnotarized. The JWST adds two optical telescopes like Hubble by making improvements in the capacity to detect and be sensitive to radiation in the infrared range. This ability allows it to dig and look further into space, deeper into the past of astronomy, bringing to light occult astronomical wonders and offering a more comprehensive perspective of the evolution of the universe. The JWST serves as a doorway into the previous phases of the universe's evolution. Recently, it disclosed something so mind-blowing that it might make you think twice about the entire cosmological model of the universe. We have discovered huge, massive galaxies at the outermost edge of the observable universe. These ancient galaxies existed only a few hundred million years after the Big Bang. The baffling aspect of the cosmic dawn is that we don't know how such enormous structures formed so early in the background of the universe. This discovery might cause us to reevaluate our comprehension of the formation and early evolution of galaxies. Examining the earliest galaxies is important for deciphering the mysteries of cosmic beginnings. The JWST can advance insights into how stars, galaxies, and planetary systems developed and changed over time. These observations span billions of years and also contribute to more general inquiries regarding the fundamental nature of the universe, including how it is structured and the factors that control its evolution. The Hubble Space Telescope was revolutionary because of the time it could spend observing the early universe. Its main limitation was its inability to effectively penetrate cosmic dust and detect infrared light from old galaxies. Hubble used visible and ultraviolet light observations, which made it difficult to explore the early universe. As these wavelengths are absorbed or distorted by interstellar gas and dust, the James Webb Space Telescope is a significant advancement. It is ahead of its time in observing galaxies from the universe's infancy, as opposed to its predecessors. The JWST is able to see celestial objects that originated only hundreds of millions of years after the Big Bang. With its sensitivity to infrared light and advanced imaging capabilities, the JWST has discovered numerous ancient galaxies with extraordinary clarity and detail, helping us understand the universe's evolutionary history. Initial findings from JWST observations have stirred a flurry of waves in well-established models of the universe. The in-depth data presents several aspects of current theories that are causing cosmologists to reconsider the fundamental guiding principles for our understanding of the structure and evolution of the cosmos. Omissions from the observed data and discrepancies with theoretical predictions have sparked ferocious debates in the scientific community. JWST observations have disclosed a greater number of galaxies at the beginning of the universe than anticipated by current models. These findings suggest a more complex and rapid process of evolution. Some early galaxies appear more developed than traditional models predict, which assumed a slower progression. The challenges arise from these galaxies' unimaginable mass and the presumed order and distribution of enormous structures. The cosmic web appears more complex and dense than originally conceived. These observations raise fascinating questions and open new paths for research. The existence of large structures in the early universe challenges existing models of cosmic structure formation, leading scientists to refine those models for a better explanation. Recognizing how these massive structures grew so quickly after the Big Bang is a conundrum that necessitates an explanation, though it does not necessarily contradict basic principles of cosmology. Considerable differences in the early universe's conditions have led to the development of new models. These differences may point to previously unknown processes, unanticipated conditions, or unidentified cosmic phenomena. Scientists have been prompted to reevaluate and improve our models of the universe. At this time, all we can conclude is that additional research is required to include these unexpected observations into a more comprehensive understanding. First, observations of the universe frequently offer exciting deep-dive vistas. Sometimes, investigation reveals differences. Early observations may show particular arrangements or properties within faraway galaxies, but closer investigation reveals changes in their structure, composition, or evolutionary pathways. In the end, massive phenomena are extremely intricate and must be thoroughly investigated before we can fully understand their true nature. Spectroscopy is one tool for deciphering the characteristics and history of celestial objects. By examining the light absorbed or emitted by astronomical bodies, spectroscopy provides detailed information about temperature, chemical composition, density, and motion. These analyses help us understand the origins and development of cosmic bodies and their contributions to the universe. Numerous cases uncovered by the JWST show that initial observations were misleading. For example, first glimpses of distant galaxies suggested a simple structure dominated by lighter elements like hydrogen and helium, aligning with theoretical expectations. However, spectroscopic analysis with JWST revealed intriguing differences elements, or compounds indicating the presence of heavier materials that were initially overlooked or misunderstood. This contradicts established ideas about the universe's origins, the mechanisms responsible for its chemical makeup, and how these elements dispersed across vast distances. Similarly, early assumptions about galaxies in the young universe were based on findings that indicated relatively uniform growth and organization, yet deeper examinations by the JWST revealed a significantly more varied and intricate mix of chemical compositions within these galaxies.